Okay, so now we're ready to go on to problem 4. And problem 4 asks, now, disclaimer, I didn't do this correct in class yesterday, but what I'm going to show you is now correct, okay? All right, problem 4. So what we ask here is, what is the pH of a 0.1 molar solution of just anion, which is NO2 minus. NO2 minus can also be viewed as base, okay? So we're just looking at base. So what I needed to do was start with this equation, which is NO2 minus plus water. We remember that from a couple videos ago when I showed the relationship, I think this was point number 4, that we have bases plus water reacting with water to then give us, except this is going to be weak, I believe, conjugate acid and OH minus. So what happens is, when we have a base, we should end up with hydroxide ions, and that's what we end up here. So we take this NO2, which is what we start with, we add water, and then we end up with one of the H's going to the NO2, and then we're left with the hydroxide coming off to be minus OH. Okay, so this is base, and this is conjugate acid. All right, so now let's set up our ice table. Initially, we know that from the information, we have 0.1 molar NO2. Water is not participating. It's a pure solvent or pure substance, so that's nothing. And then for HNO2, we don't have anything yet, and then we don't have any OH yet. So the change, so that's initial. The change is, this is a weak base, so it's minus X, so it partially dissociates, which means that this is plus X and this is plus X, to then give us the equilibrium concentrations to be 0.1 minus X plus X and X. So the concentration for OH is going to be equal to X when we solve for X. Okay, so we have this information. Now we're talking about base. So that means that in order to solve this, we need to use the equilibrium, the base ionization equilibrium constant, which is Kb. And Kb is equal to the products, HNO2, the conjugate acid, times OH minus over NO2 minus, which is our base. Okay, good. Now, how do we figure out what Kb is? Well, we know what Ka is from the previous question. So we have a relationship. Kb times Ka is equal to Kw, right? We recall that from a few videos ago. So that means to solve for Kb, all we have to do is put in Kw over Ka. So that would be equal to 1 times 10 to the minus 14 all over 4.5 times 10 to the minus 4. And then that gives us a Kb of 2.22 times 10 to the minus 11. You also could look this number up in one of your tables, I think, as well. So remembering that we're open book, we can figure that out. but this would be how you calculate it. We know that the Ka from the previous question was 4.5 times 10 to the minus 4. We put that in, and then we solve for our Kb. Now we have all the information that we need so we can solve our problem. So 2.22 times 10 to the minus 11 is equal to x times x over 0.1 minus x. We're going to make an approximation. We're going to assume that x is a whole lot smaller than 0.1. And why can we make this approximation? Well, we have to make sure that it's valid first. So in order to verify if it's valid, we have to take the Kb over the initial base concentration to figure out an approximation for what's dissociated. Because remember over here that OH is about equal to the Kb concentration. So for figuring out percent dissociation, we can substitute OH minus for Kb, and we have our initial base concentration of 0.1. So Kb is 2.22 times 10 to the minus 11. And NO2 is 0.1 times 100. So then we calculate our percent dissociation. I don't remember if I did that, so let me make sure or whether or not this is valid. And we definitely know that it's super small, 2.22 times 10 to the minus 8. So that's super small. Now, I should have just known off the bat, now that I think about it, because this value is 10 to the minus 11. Before, we were able to know that if we put Kb over the acid concentration, not Kb, Ka is 10 to the minus 4. When we used this value, we got 0.45% dissociation. So that number, this number is even smaller. So we would obviously get an even smaller number. So our approximation is indeed valid. So we can then do this. So that would give us, that takes us to 2.22 times 10 to the minus 11 to be equal to x times x over 0.1. We then solve for x, and we find out that our x is equal to 1.49 times 10 to the minus 6 molar. Okay, so that is equal to, here's our x. X is equal to the OH concentration. So OH is equal to 1.49 times 10 to the minus 6 molar. Which then gives us the chance to then calculate POH, which is equal to the negative log of 1.49 times 10 to the minus 6. And then we end up with 5.83. Now we're at POH, and we need to figure out pH. So all we have to do to get to pH is take 14 and subtract by 5.83, and then that gives us 8.17. And we are finally at the answer. Now, let's think about this for a second. We're considering conjugate base, which is NO2 minus, or a base. We know that bases have a pH normally that's higher than 7. And indeed, we have a pH that is higher than 7. So this answer makes sense.